Hello and welcome to this video on extracting just about all of the ethanol that can be fermented or produced in any kind of chemical reaction. A pot still can extract up to 60% of the ethanol from a wash. A column still can extract about 95% of the ethanol. Somehow there is a way to extract 99%. The reason we say somehow is that ethanol is an azeotrope. Azeotropes are chemicals that resist more as the concentration in water goes down, basically an inverse relationship between amount left and difficulty in separating. For most day-to-day businesses, this is not a significant concern. The amount of ethanol left over in a fermentation is honestly not practical given the difficulty in extracting it. While getting 100 litres instead of 95 litres might be nice, those 5 litres are not worth hundreds of dollars of material, time and expert employees at the best end, and at the worst end, thousands of dollars. For other chemicals, it can be quite worthwhile. Think of pharmaceuticals, chemical and biological reagents, cleaning for water, and more. Azeotropes are interesting, and we say interesting purely because of how they work. Each of them has a particular boiling point that it's characterized by. The boiling point of the azeotrope is either going to be less than the sum of its parts or more. Where the boiling point of the azeotrope is greater than the boiling point of the things that make it up, it's a negative azeotrope. Where it is less than the boiling point of the things that make it up, it's a positive azeotrope. While ethanol is not the best example, it is perhaps the easiest to understand. You often get a fairly straightforward mixture of ethanol and water, somewhere around 95% ethanol and 5% water. The boiling point of ethanol is 74.8 degrees Celsius. Water is well known to boil at 100 degrees Celsius. When you put the two together at the ratio mentioned, it begins to boil at 78.2 degrees Celsius. This is below both the point at which ethanol and water will boil. This means you can't extract either of them as separate chemicals. You can only extract them together. And this is why, as mentioned, you don't have the ability to extract that last 5% of the ethanol. You can, however, use different methods to get ethanol out of water completely, or separate water away from ethanol. It depends on what you want as the end product. This is a process called azeotropic distillation. The way it works is surprisingly simple, but also much more difficult remembering what happens with azeotropes. The way you get around this is by adding a third chemical, or at least in the case of trying to extract ethanol from water. Often something like benzene is used. The addition of this third chemical means that you can shift, for the most part, the boiling point of the azeotrope just over the point at which ethanol would begin to boil off. This means that you can extract that while leaving the rest of the contents relatively untouched. You have, for all intents and purposes, shifted the volatility of the reaction so that the ethanol is the most volatile compound whilst everything else is much less volatile. And this is what allows you to extract the ethanol while leaving everything else behind. The next method used, again using ethanol as an example, is a method called pressure swing distillation. And this relies on the fact that there is a gradient of the chemicals involved in making sure that you can't extract one without extracting the other, because this is what causes that shift in the point at which everything boils off. By having it set up in just such a way that the distillates have a boiling point where they just cross over, you can effectively separate one and the other out by using their individual characteristics. Water doesn't vaporize into a gas as readily as ethanol will, and so by altering the pressure of the environment in which you are working this particular reaction out, you can force it to favor the separation of the two. And this is exactly what's happening in pressure swing distillation. The fundamental idea is that you have ambient pressure, or general atmospheric pressure, going in both directions. This then allows you to set one of the directions as being at a lower or higher pressure. For example, By increasing the pressure, you can force water to fall out of the gas-type suspension and ethanol to continue to remain as a vapor. This allows you to separate it out both physically and chemically. In order to maximize the yield from this, it's often done with two different columns, one being low pressure, the other being a high pressure system. Generally speaking, you use two columns to ensure you get maximum extraction, or perhaps it would be better to say separation, of the constituent parts of the azeotrope. Generally speaking, what you'll find is that low pressure extraction has the alcohol or ethanol come out the bottom of the column, and the water flow off and go back into the reaction, whereas the high pressure system causes the ethanol to evaporate out the top of the column and then get condensed and carried off. Together you can get 99% extraction of ethanol, although some systems can get even higher values. Compared to the first method of extraction, this doesn't require any additional chemicals, and that's certainly an advantage, although you do require some very specialized equipment and familiarity with using it. Using a regular distillation column is dangerous. Using a high pressurized column full of explosive ethanol in larger volumes is very dangerous. The final method we'll mention is chemical action separation, and this is done using the properties of the different things again, for example, water and ethanol. Different parts of it, like the water, have different affinities for other things. By taking advantage of that greater affinity, you can fundamentally have them grab onto this other thing and leave the ethanol entirely alone. A simple example of this is something like calcium oxide. That can be used by being added to the water. The water will form a more complex chemical with it, but it's a non-volatile compound that will separate out, called calcium hydroxide. This can nearly all be removed by using a filter setup. The filtered material can then be distilled, and by distilling it, you can get practically 100% pure ethanol. The other advantage is that the chemicals involved are relatively inert, at least initially, so they are, at the start, entirely safe to handle. The advantages of doing this is that there are different kinds of chemicals that can be added to your azeotrope, so not just thinking here of water and ethanol, something like water and diethyl ether, and in fact many other different kinds of azeotropes can be dealt with using a wide range of chemicals, and this means that it is much more flexible in its approach, and therefore more applicable to more scenarios. The downside is, you do need to be familiar with what you're using, understand how to apply it and what to apply, and the means of disposing of the waste at the end. As you can see, getting that last 5% of the ethanol in just a water-ethanol azeotrope is difficult. Not impossible, but difficult. You need to be able to take advantage of the different chemistry of the alcohols and water that you are trying to separate out, or in fact for any other kind of chemical that you are using. This process is especially important when we talk about laboratory reagents that are anhydrous. That is, they have no water in them, or at least well below 1%. This sort of method is needed for that. There has to be a way to extract all of the water out, and water tends to want to stay right where it is when you least want it to. Thank you for watching this video. If you have found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions you have below.